In watching a video on math education, I began to realize I did not agree with what was being spoken and wanted to challenge it without dismissing the topic altogether. In my own education, I learned to do the following: explain what I was taught, then challenge what I was taught, look for patterns, then explain the patterns, apply my understanding in solving some problems, solve the problems using a different approach, and then challenge your explanation and understanding of what I've done. Zero is often said to be nothing. I don't really believe this to be true. Okay. Zero added to A gives us A because we result in no number. We result in the same number. And zero multiplied by a number gives us zero. This is what would lead us to draw the conclusion that zero is nothing. But if we take and raise 2 to the 0th power, we would expect to get 0 because exponentiation requires multiple multiplications. And similarly, 0 factorial would be expected to be 0 because factorial involves multiple multiplications also. But in truth, 2 to the 0 is 1, and 0 factorial is 1. Now, let's look at an interesting pattern. A times 1 is equal to 1. Very similar to the pattern that A times 0 is equal to 0. But in this case, we choose to note that when 1 multiplied by number results in the number, it's because 1 is the identity element for multiplication. And it turns out, parallel with the 0, 1 to the 8th power is 1, as 0 times A is 0. However, to give some consistency, it might be better to interpret 0 being added to A not as 0 being nothing, but 0 is the identity element for addition. Now, think about this for a while, because any new concept that is contrary to an old concept, we want to try to understand why the difference. And you're going to have to go over and over this again before it becomes apparent. Now, let's look at 0 in a different way. What we're going to do is note that 1 can be used to create numbers. So for the number 3, we add 2 to the previous number. For the number 4, we add 1 to the previous number. Well, in the case of 1, the previous number is 0. So 0 plus 1 would be equal to 1. Now let's do a proof. Proof is basically making some statements and then explaining each of those statements and deriving new statements from the previous statements. So 0 plus 1 is equal to 1, because that's how we create our numbers. We also could say the same thing for 3 is equal to 2 plus 1, but we're going to write it as 1 plus 2. This is called the commutative property. We interchange numbers, and we basically learn that property by observation. Now, if we take the 1 and replace it by 0 plus 1, we get 0 plus 1 plus 2 is equal to 3. If we now reassociate our numbers, so instead of adding 1 to the 0, we add 1 to the 2 first, then we get 1 plus 2 can be replaced by 3, and we get 3 is equal to 0 plus 3. So without saying anything about 0 being nothing, we have shown that with the assumption that 0 is the number before 1, that we get the same results. Now, let's look at some conflicts that we get with either of the two ways. Here we multiply 3 times 2, which means adding 2 3 times. 2 times 2 would be adding 2 2 times. We seem to be dropping a 2 each time. And adding 1 times 2 would be 2. What would 0 times 2 be? Well, if we drop the 2, we get a blank. But also note that we were dropping plus 2s, and in this case, we're dropping a 2. But let's now redefine multiplication. By putting 0 in front of the multiplications, we would still get the same result. But as we're dropping our plus 2's, we're left with a 0. Now, we can always find some kind of problem or inconsistency with examples. That's why we want to look at problems more than one way. So if we look at 3 times 2, what we could do is we start with 2, jump to 4, then jump to 6. And notice that in this definition of it, that 2 is our starting number. If we come over here and look at the same multiplication with 0, we start at 0, jump, jump, and jump. 3 jumps, 3 pluses. In this case, we only had 2 pluses, but very often that this example will be associated with this. And now we see why it doesn't make sense. So an explanation now is having our mind look at something that is contradictory, which could get us in trouble later on. Okay, now, in order to justify 0 as being nothing, they talk about it as a placeholder. Okay, now, we could have a placeholder, we could just leave a blank there or put some other symbol there, but blank seems to be more reasonable with our upbringing. So this would be 4 times 100 and 4 times 1, which would give us 404. Now, if we put a 0 in there, we get 4 times 100, 0 times 10, 4 times 1, and that gives us 404. Sort of a nice way to write it. And that seems to be consistent. But this implication is that 0 is unique as a placeholder. Well, any number could be a placeholder. We put a 1 in that space, we get 414, but we still have that 4 moved to the hundreds place. Okay, so I feel a little bit uncomfortable with that, is that, the way we run it, but let's see what happens with 0 again. If we put 0 after a decimal point or before a decimal point, we get a number that's smaller or bigger than our original number. So a little bit questionable about what we mean by placeholder and not changing something. On the other hand, we could also write numbers in this form where I use a separator. I put 4.2 in the hundreds place, minus 2 in the tens place. And when we do this, 4.2 times 100 is 420, minus 2 times 10 is minus 1, and I get 404, not using a 0 at all. Now here's the challenge. What would we do about 0.001? Well, with a little playing around, I discovered we could write it as 0.1 minus 1 minus 1, where there should be a separator between each of these. Well, the first one is 1/10. The next one is 9 100ths. You'll see I made a mistake. That should have been minus 9 minus 9. Okay, so we'll correct that. But that then becomes 9 minus 900 minus 9,000, which gives us 100 minus 90 minus 9, which is 1,000th. Really nice. Okay, now another misconception comes about that 0 doesn't have a sign. It's either plus or minus. Well, let's take a look what happens with this first and a discovery we make. We want to find out what the numbers before 0 are. So A is the first number before it, B is the next number. So A would be B plus 1, and 0 would be A plus 1. This is how we create our numbers. So starting with A plus 1, if we subtract 1, we get 0 minus 1. And I'm going to just drop the 0 and make it minus 1. This is sort of notation when we get something to represent something else. If I start off with B plus 1 is equal to A, add 1 to both sides, that allows me to get A plus 1 is 0. And now we get B is equal to 0 minus 2. And using the same notation, that becomes minus 2. And if we now substitute minus 1 in for A and minus 2 in for B, we get minus 1 plus 1 is equal to 0, minus 2 plus 2 is equal to 0, and we've just discovered the definition of a negative number. And if you think about it, you've never been given the definition of negative number. You've just given a description of them. This is also true of fractions. Now, 0 plus 0 is equal to 0. We can come about that in several ways, but let's do it the assumption that when 0 is added to a number, we get that number. Well, if we subtract 0 from both sides, we get 0 is equal to 0 minus 0. Well, notation-wise, this should be minus 0. Now, normally the equal sign is interpreted as sameness, but in this time we're going to talk about equivalence. Okay, so what we're saying is our interpretation is that 0 and minus 0 occupy the same place on the number line. Sort of like 0 is the beginning or end of the negative numbers, and 0 is the beginning of the positive numbers. Now, sort of try to see if we can resolve what's appearing to be a conflict in our mind. If we take 1 over 0, which is this function here, 1 over x, as x becomes smaller, 1 over x becomes larger. So 1/2 inverted becomes 2, 100 inverted becomes 100, 1,000 inverted becomes 1,000. So as we get closer to 0, this becomes bigger and 0, bigger and bigger. So that makes sense that 1 is equal to 0 over infinity. But we could have started from the other side, which I didn't realize until I had done some reading. And if we take negative numbers and they get minus 1/2 is inverted is minus 2, minus 100th inverted is 100. So it approaches negative infinity. Well, it turns out this can help us resolve this, because if 0 is equal to minus 0, and I substitute minus 0 for that, I now get 1 over 0 is minus infinity. So we're now looking at this in a different way and showing how we resolve this. Should we stop teaching that 0 is nothing, is a placeholder, and has no sign? Mathematicians do not like to be shown that they do not understand mathematics. Mathematics has an evolutionary history of slowly accepting new approaches or new concepts. Others have probably observed parts of what I have shown you already. However, by teaching both concepts together, we can strengthen our understanding and confidence in mathematics. It also does not disrupt the way we teach math now, a major problem which occurs every time we try to replace what we have been taught previously. You may notice that I have tried to find errors in my approach. It turns out that the definition of 0 is the integer before 1, not the number before 1. I and my students discovered the problem in 2 ways. 0.5 is the number before 1, and non-integer multiple arithmetic. We have to scale non-integers to integers, radians to degrees, for this to work. The challenge is yours.